Shai Ben-David, who's my colleague at the University of Waterloo. Shai is really one of the OGs of ML theory. He's been doing this stuff since before I was born. I think so. And he's done a lot of really impactful and influential work, some older stuff on domain adaptation before we realized how important and significant this type of problem would be. Recently, he's been more interested in these sorts of problems involving, say, robustness, fairness, privacy, stuff like this. He's made some really good contributions, and it's been great working with him so far. He's going to talk about some stuff we've done together on private distribution learning with public data. Without further ado, go ahead, Shai.
Thanks. Yeah, so this is a joint paper with Alex, Clement, Gautam, and Vikrant. And this is, I mean, the leader on this project was Alex. It's basically his master thesis, and he did great work on this. So, yeah. Okay, so what are we going to talk about? We're going to talk about distribution learning and distribution learning in the context of privacy, and furthermore, distribution learning in the context of privacy when you also have access to some public data. So it's trying to learn a distribution. You have a sample from a distribution. You're trying to figure out what the distribution is. You have a knowledge of some class of distribution from which this distribution came. Otherwise, you're in a overfitting, no free lunch situation. And you're trying to do it privately, not revealing your training data, with the access to some public sample points. So that's what we're talking about. Okay. So we started the problem of private distribution learning with access to public data, and we call it public-private learning. So the learner is given some public data and some private samples. They are drawn from an unknown distribution, and there is a class, capital Q, that is known to the learner. And for simplicity, we assume that the generating distribution belongs to this class. And the goal to the learner is to get an estimate of this P that generates the data while protecting the privacy of the private samples. So there's public samples, private samples. We want to protect the privacy of the private samples. Okay, so why do we need it? What's the motivation? That there are many tasks which are simple to do without privacy constraints, but we can prove that once you impose privacy, it becomes impossible to do it. So either you require much more data, or it becomes completely, you cannot give any guarantee of success because of the privacy concerns. So the prototypical example is you're trying to learn a d-dimensional Gaussian distribution from samples, even on dimension 1. So you have just a Gaussian over the line, and you are trying to learn it, and you cannot do it privately. You can prove that this cannot be done privately unless you know some bound on where this Gaussian is living. On the other hand, if you don't worry about privacy, then it's very easy to learn Gaussians. You need the order of d-square examples. So we know that no finite samples will allow you to do privately the task of learning a Gaussian, although without privacy requirement it is very easy. So the question is, how can we formalize the type of data and quantify it that turns a task into doable with differential privacy? What is the amount, what is the information that we need to turn it into privately doable? So in the case of Gaussians, we know that if I can put a box, a bounded box around where the Gaussian lives, then I can turn my problem into differentially private. So actually all what distracts the privacy is that I don't know where the Gaussian lives. And the question is, how do we quantify such crucial information, the information that disrupts the privacy? So the way we do it here is we quantify this information by using non-private samples. So we assume that you have also access to samples which are not private. So for example, I want to train some classifier, some distribution learner, and maybe I'm offering people some tokens if they agree that their data will not be private. So maybe I can gather some non-private examples, and the question, and this is a way to quantify what is the data that kind of creates this gap between learning without privacy and learning with privacy. So we want to leverage small quantities of public data to privately learn from sensitive data, even if without this extra public data, this task is impossible. So this is the question of, was the focus of a previous paper by Alex and Gautam and Signal, and now we are following up on this work and making, you will see what we contribute in this work now. Okay, so we, of course, we need the basic definition, and the basic definition, I mean, is what you expect intuitively. So we have a learner, which is an algorithm. The algorithm is trying to learn a distribution, so you get a sample from the distribution. But we assume here that the sample comes in two batches. One, x to the m, is a batch of data that we don't care about its privacy, and the second part is a batch on which we do care about the privacy. And what the algorithm outputs is some distribution, because we're trying to learn a probability distribution. And what we want is that it will be private in the second parameter, in the parameter that takes the data that we want to keep its privacy. So this is a public-private algorithm, and we say that a class of probability distributions is learnable in this public-private data if we can get such an algorithm that we use and many public examples, and then a sample of size n, which is its privacy is preserved, and it will output, the output of the algorithm will be close to the true distribution that generated the sample. So that's kind of the basic, I mean, it just follows the intuition of what do we mean by public-private learning.
Sorry, one disambiguation. You have like X, data sets X and X. I guess one should be like X and X prime or something.
Oh, this is, right. This should be X prime.
Yeah.
It's not, I mean, this is a sample from the distribution. This is the independent sample from the distribution. Thank you. Yeah. Okay, so now we say that a class is privately private learnable if we have such an algorithm that will meet these parameters, and we omit here when the class, we usually omit the number of public data that you want, but of course it will only be interested in the case where the number of public examples that we need would not have sufficed to learn it without the private data. But when such a situation exists, we sometimes don't mention the size of the public data. Okay, so let me go briefly over the main results. There are lots of results in this paper, in this work. And maybe the most conceptually interesting result, not technical, is that we show equivalence between three different notions that seem kind of vaguely related. One of them is learning. We learn a distribution either in the total variance distance or in the parameter estimation. So one aspect is learning, another aspect is sample compression schemes, and the third aspect is the notion of least learning. And what we are going to show is that all of those are equivalent. So the main conceptual contribution here is to show that public-private learning is equivalent in some quantitative way to being able to do sample compression of distribution, and this in turn is equivalent to least learning. So I will now, I will soon explain exactly, I guess we already explained what is the learning task. I will explain what is the compression scheme, what do we mean by that, and what do we mean by least learning. But all those three tasks turn out to be quantitatively equivalent. And with this tool, we will be able to get all kinds of improvements to previous results. So here is some examples. These are samples of the results that we can get. Using those tools, we can get the private-public learnability of a mixture of Gaussians in D dimensions. So you see that the public size, the size of the public data that we need is K is the number of distributions in the mixture. D is the Euclidean dimension of where the Gaussians live, and alpha is the accuracy parameter, the total variance between our output and the true generating distribution. This is the number of public points. This is the number of private points. And what one needs to notice is that, first of all, you could not learn Gaussians privately without this public data if they were arbitrarily placed. So it is meaningful. This part does contribute something meaningful. The other thing to notice is that this is below the lower bound that is needed for learning a mixture of Gaussians. The lower bound for learning mixture of Gaussians will have a square here and a square here. So the number of public data that we have is really not sufficient on its own, and it does enable you to learn privately with a number of examples that is like learning without the privacy constraint. So with few public data, you converge to the ability of learning if you were not concerned about privacy. So that's one result that we get with those tools. Another result is that if we just want to learn a single Gaussian, this result is interesting mathematically, not so practically, but mathematically it's a very kind of nice result. I can give it compliments because it's mainly the work of Alex, so I'm not complimenting myself. For learning a D-dimensional Gaussian in RD, there was already an upper bound by Alex and Gautam, and the signal that showed that you can do it with D+1 many sample points. And here we get a lower bound of D points. So we know exactly how many public data you need in order to learn a Gaussian, a single Gaussian. Another result is that rather than, you see, so far the results that we talked about in most of the literature on private public learning is talking about learning specific families of distributions, like mixture of Gauss. Here we have a very general result that is VC dimension based. So we have a VC dimension based on the public-private learning for any class. It's general result. Of course, what are we looking at the VC dimension of? We're looking at the VC dimension of as a class which is called the actors class, and that's the class, if you have, Q is a class of distribution. Q is a class of probability distribution. For every two distributions in Q, we look at the points, the set of all points on which the density under F exceeds the density of over G. So for every pair of distributions in my family, I get here a set. So when I go over all pairs in the family, I get a collection of sets. So that's a collection of subsets of X, and we can talk about its VC dimension. So it turns the task, you have a class of distributions, and it extracts from this class of distributions a notion of a VC dimension of a collection of sets. And if this VC dimension of this collection of sets is finite, then we can use it to learn with this public-private setup when the number of public data is just O of D over alpha. Here D is not the Euclidean dimension. Here D is the VC dimension of this actors class that's generated by my class of distributions. So that's a general results, in contrast to most of results in this area that we're talking about specific distribution. And yeah. What?
If Q is a set of Gaussian.
But if Q is a set of Gaussians, we can compare this to the previous results. This is weaker than the previous result.
Okay, and
this is an upper bound, and if we try to apply to Gaussian, it gets a weaker result.
Yeah, and these sets would be what, ellipsoid or hyperplanes? These sets would be ellipsoid?
These sets will be, what is it? I don't see.
What do they look like?
Oh, they're very complicated.
Okay.
So, no, really. I mean, like when I started working on the problem of random distributions with Hassan Ashtiani, like, I don't know, many years ago when he was my student. And this was the first approach that we were trying, no privacy, just using this approach to learn. And we got some results, but they were much weaker than the later results that we got with compression. So for the concrete case, just to repeat the question, for the concrete case of Gaussians, we get better results than the result that is implied by this. It's very difficult to understand this class for mixture of Gaussians in high dimension. Yeah. Yeah, it's a good point. Okay, so we were going to use, I will just mention two technical results that were there before. One of them is that if we have a class of distributions which is finite, then we can learn it privately. And the number of examples that we need is roughly log of the size of the family. So if the family is finite, there is no news here. We can learn it in private, but in differential privacy. But of course, if we look at class of distribution of Gaussians, it's an infinite class. So that's one key point, that once we reduce things to a finite class, we can learn it privately. The other key point uses this Alcatraz class that we talked about a minute ago. And it is known that if this has a finite dimension, then one can learn, again, without privacy. So the two key results from the previous words that we use, one is that if you have a finite class, then you can learn it privately. And the other one is that if you have a class with a finite VC dimension of this finely induced class, then you can learn it without privacy. And we are going to use both of those techniques. Okay, so the next thing I want to talk about is, I said that we are showing the main power tool that we are using is this equivalence between private public learning and compression and least learning. So I want to talk a bit about what is the compression scheme for distributions. So the compression framework is like this. We have a class of distributions and say Gaussians or mixture of Gaussians, and some distribution is picked from this class, and this distribution is going to generate our data. This is distribution that I denoted by P before. Now we have Alice that knows everything. She knows what the distribution is and what is the class. And we have here a learner, Bob, that knows only what is the general family of distributions. He doesn't know what D is. Now they're playing a game. So Alice gets a sample, which is IID sample drawn by D. And what Alice can relay to Bob is only few of the points that came up in the sample. So we say it's a T compression scheme if she only passes on T many of the examples that were randomly drawn. Not arbitrary points of her choice, but just a subset of what was drawn randomly. And now we want that Bob, just seeing this, will be able to come up with an approximation to the data generating distribution. So we call it a compression scheme of size T. If there is such a mechanism that allows Alice, no matter what sample she gets, to extract at most T points that will allow Bob to learn from those just T points. That's the sample compression scheme from distributions. So here is an example. say we want to learn a single Gaussian on dimension 1. What are we going to do? So you see, if I draw such random examples, and I'm Alice, and I know what the Gaussian is, and I want to pass to Bob only a few examples, I can pick 2 examples because I know what the distribution is. I can pick 2 examples, such as the average is roughly the mean, and the difference over 2 is roughly the variance of this distribution. This is, I'm Alice, I know everything. The main thing is that if I have enough, large enough sample, I can find such 2 points that will allow Bob to recover both the mean and the variance. So for Gaussians on the line, on the dimension 1, we can get a compression scheme of size 2. And the main result here is that if you have a compression scheme, then one can learn in a sample efficient algorithm, and furthermore, one can learn in this private public setup. So what is the connection? How does this connection work? The idea is that assume that I have such a compression scheme between Bob and Alice. And now I'm trying to learn, and I don't have Alice that knows everything. I'm just the ignorant Bob. What am I going to do? I'm going to simulate all t-tuples that Alice could have sent me. For each such t-tuple, you see, Alice, I know that there are, I draw a sample. I know that there are t-points in the sample such that if Alice sent them to me, I would be able to recover the distribution. But I don't know which are they. So I'm going to simulate it on all t-tuples from the distribution. So I'm going to generate a family of candidate distributions, depending on the different t's. But the size of this family is only the number of t-tuples from the original sample. And I get a finite family, and if I have a finite family, I can learn it privately in sample complexity that is log of this size of the set. But if the original sample was of size n, I get here only n to the t many candidates. I take log of it, and basically I am able to learn it in private. So what I'm explaining here is why having a compression scheme allows you to learn in this public-private situation. And now the big advantage of compression schemes is that they are modular. You can work with them very easily. So for example, if now instead of learning, we saw that we can have a compression scheme for Gaussians on the line. But assume that now I have a mixture of Gaussians, compression scheme composed very easily because if I get a sample from this mixture, what Alice can do is pick 2 points for each of the components. Alice is all-knowing. She knows what the components are. So it turns out that if I have a sample compression scheme of size t for some distribution, and I look at all k mixtures of distributions from this family, I get compression of size just k times t. Because you see that now all you need, if I could learn, if it's a k mixture of distributions from the family F, and each of them could be compressed to t many samples, then I compress the mixture to kt with some additional factor because I have to tell Bob which of the kt points can belong to which distribution. So this is modular in the sense that you can compose, you can get mixtures if you can learn a function class F. And furthermore, I don't have in a slide, it is also composable to product distributions. If I have a product of distribution that if each of them has compression to size t, then I can learn the product because Alice will give you t points from each coordinate. And you will be able to recover the whole product distribution. So the advantage of working with compression is it allows you to combine two mixtures and to high dimension. And this is the main tool that we use in the work with Hassan on learning mixture of Gaussians without privacy. But what we notice now is that this framework also allows you to do the public-private learning because it reduces the task to a finite class, and a finite class can be learned privately. Okay, so the last component that I'm still missing is the component of list learning. Because we said that we show equivalence of 3 types of learning: distribution learning, existence of compression schemes, and public distribution learning, existence of compression scheme, and list learning. So what is list learning? List learning for a class of distributions is you have your class of distributions and you have some parameters, and you have another parameter, which is the length of the list. And what the algorithm does is the algorithm takes a sample and he generates a list of candidates. So L is the list of candidates, and this list of candidates is of size at most this script L. So rather than outputting one distribution, the learner here is allowed to output a list of L distributions. So the task is a bit easier. And what we want to guarantee is that the distance between the true distributions and the list, the closest member in the list, will be at most alpha with high probability. So then we say that the class is least learnable. Okay? So what we now claim that all those are equivalent, and we are using the compression is the tool that allows us to get positive results. And to get the negative results, like to get the results that you need at least D many points in order to learn a Gaussian in RD, we use the difficulty of learning a list. So I think this is the end of my slides because I didn't want to get into any proofs. But what I want to show you, or to give an idea of how come those 3 are equivalent. So what we want to show is, first thing we already discussed. If you have a sample compression scheme, then you get public-private learning. Because if you have a sample compression scheme, you can reduce your problem to learning a finite class, and you can learn this finite class privately. Now, why is public-private learning imply list learning? Because if you have public-private learning, you can generate a list. You look at the set that you need, training set that you need for public-private learning. Then the algorithm will generate a list. And then from this list, you will give Bob, Alice will give Bob the index of the member of the list that is closest to the target distribution. So what is the size of this compression? We need first the training data for the list learner, and then we need log of the length of the list in order to tell Bob which member of the list is the true one. So if we have this kind of list learning, we can get a public-private learner whose public size is just the size of the data needed for the list learning. And then the last component is why, if we have list learning, we get compression. I know I showed you what are we missing now? And now I got myself confused. Right, public-private implies list learning, right. So the public-private implies list learning is that what you do is you take the public data, and for every candidate, this is not an algorithmic thing, it's only conceptual. For every candidate Q, you ask, if I had independent samples from Q and I feed it to my algorithm, will I get something which is close to Q? And you only collect the Qs that will recover themselves, then you get a finite list. So all those 3 components are equivalent, and we use it to generate all kind of better upper bounds and lower bounds on private public learning than they were there before. So thank you.
Yeah, we have some time for some questions.
Yes.
So was the equivalence between compression schemes and list learning known before? Like if I just...
don't think so. No, I think that's the compression to list learning. No, I'm not aware of this equivalences being investigated before. The part that was known was that compression allows you to do learning, and then a closer examination of it shows you that it allows you to do public-private learning. That was the part that was known before, but the other components were not. Yes.
Yeah, sorry, this is kind of a basic question. I'm trying to parse this expression. So how do you compare the distance of a distribution to a list of distributions?
No. Okay. So the reason I'm using distance here is that this applies both to total variance distance or to parameter estimation, no matter what distance you want. Now, what do I mean by a distance between a distribution and a list? This is a list. The algorithm takes the training data and outputs a finite list. So the distance between a distribution and a list is the distance between this distribution and the closest to its member in the list.
Okay, thanks.
Any other questions? Yes.
Maybe I'll ask one. I'm not so sure. But so the way you presented it was that we need to have, let's say, M public data points and then a bunch of private data points.
Right.
But if you're going from compression to this public-private learning, does it matter? Like the way I understood it is that, compression, you would probably need maybe those M data points to be some of the points that are giving you the compression to give you, an idea of where it lies, and then you use private data points. So just trying
Oh, no. Yeah. What is the private and what's the public here? So the public is those M points that allows Alice to give you a compression. Now I am Bob. I use those M points and I get a set of candidates. But now I have to choose between those candidates. And in order to choose between those candidates, I need to generate more samples to ask which of them is the best. And this part is being done privately.
perfect. Thanks.